Hope you guys are not too upset about the midterm. Okay, I know it's kind of challenging because right now we're doing this remote class, and then the well, I would say the quality of the class is not as good as before. But then don't worry too much because all the score will be curved as I explained before, and then all of you should be fine. And then it's interesting saying this is that I don't know if you guys saw the news. Actually, yesterday I think the Nobel Prize of Economy was given to auction theory, which is really weird. And then it actually reminded me of the game theory that Nash won, famously won the game theory, and they actually related to the midterm or any exam that is curved, right? Because if you guys are allowed to communicate with each other about the strategy of the exam, which is allowed, right? You're not allowed to exchange, your answers to the question, but then you can exchange your strategy. And then any exam that is curved, okay, you can say that why don't we agree on, for example, 50 points, right? All of you finish 50% of the exam, and then that way, you guys can all receive A because you're as good as the best in the class. Okay, but then the game theory also told you, okay, how much can you trust your friends? Okay, how do you know that he or she won't, score 10 points more, and then he or she become the first, and then the rest of you receive a B, and it's kind of interesting is that with the if the size of the class become larger, it's more and more difficult to reach agreement on this, and eventually what happened is that all of you would just do your best and then get the highest point as you can. Okay, anyway, let's come back to quantum mechanics, and this week we're going to talk about a content that's normally not taught in undergrad level quantum mechanics, but then the math itself and then the physics itself is actually kind of on the same level as the rest of the quantum mechanics. So I think it's actually useful to teach it here in this class, and also it actually ties into in a second half of this class we will have quantum communication, which primarily use photons. So I think it's better for us to to get a straight idea of what light is in quantum mechanics. Okay, and then the second thing is about the quantum computing. Okay, so probably some of you read some news or read some reviews. You will know that there are tens of quantum computing platforms. Okay, there are superconducting Joseph junctions, which are used by Google, and then I think also by Facebook or Amazon. Okay, all of those, and then also IBM is also using those, and that are the most mature platform currently for quantum computing. And then the qubit, the Google did last year was 54 qubit. And then that's one physical system, and then there are other physical systems, for example, cold atom, trapped ion, cavity QED, and then even topological insulator, which was right now is, I think Microsoft is kind of into this. So as an undergrad level class, it's very unclear, okay, what system should we talk about, because for every of those systems, if we want to really understand how they work as a qubit or how they work to do quantum computing, we probably need 1 or 2 weeks just to introduce a system. So that it actually makes sense for us to just not talk about them at all, because we can wait until one of them win. Okay, but then one thing that's very clear in the field of quantum computing, communication, and quantum sensing is that you will always use light in terms of communication, right? Because light travels at the speed of light. That's the fastest thing on Earth. So that currently, I think that's, well, let me think about it again. I think currently that's the only carrier which can actually transport quantum information, okay, from point A to point B. And for electron, I think you need to cool the electron to superconducting temperature, which is economically not a good idea, okay, and then also there's no point of doing that if you have photons. So photons will be used in quantum communication or quantum information, and then will be used in the future for quantum networking. Right now we connect computers with the internet, which already use light, and in the future, if quantum computing really become the dominant computation unit, then of course to connect these quantum computers you need a quantum network, and that will also use photons, also use light. Okay, so so that's actually the reason that we're going to talk about the quantization of light. Okay, to tell you what exactly is a photon. Okay. Okay. So coming back to this, the second reason that we go into light is that if you think about it, the quantization of light actually represents a very different approach compared to quantization of electron. Because for electron, what you have is you have position. Well, in classical mechanics, you have position and momentum, right? And then you use those to calculate energy, calculate angular momentum, so that the process of quantization is not that different. So the quantization for electron is to change x and p into operator. Right. That's the way you do quantization. Okay. And then in terms of light, we're actually using a very different. Well, not very different. We're using a different way of doing the quantization, which at first looks a little bit weird, but then later it was proved by experiment that it actually works. And then also later you will see that it's very interesting is that the light after quantization become photon, and it is exactly the same in a mathematical form. Is exactly the same as a harmonic oscillator. It's very simple, elegant. And then that's exactly the same as a sound wave, like phonons. Okay, and all of those, and then also the same as LC oscillation circuit, which is probably the easiest, the simplest circuits to build a microwave oscillator. So all of them are actually the same mathematically, and then so doing this for once actually can apply to many systems. So to do the quantization of light, we have to answer first what is light in classical mechanics, right? And then the answer is quite straightforward. It's Maxwell equation is light, right? So light is oscillating electrical and magnetic field. Okay, the light itself is field. Okay, it's wave, it's field. You don't need to quantize it to become a wave, right? Itself is a wave. So for light, okay, what you have is you have Maxwell equation, and then the first one is Gaussian law for electrical field. Second one is Gaussian law for magnetic field. And then the reason it equals 0 is because there's no magnetic monopole. And then the curl of the third one is Faraday law of induction. That actually is a reason that we have electricity these days. Okay, it's the varying magnetic field generate electrical field. Okay, and then if you have think about it as a motor, right? The motor rotate, and then if the rotor have magnetic inside, and then you change the magnetic field, and then you generate electrical wave, and that's the current, and you generate electricity. And then also you have the reverse is the Ampere's circuit law that says the varying electrical field will also induce a magnetic field. Okay, so this is a Maxwell equation, and I'm guessing all of you are familiar with this, or at least heard of this. Okay.
I recognize all of them except for the last one. I think is new for me, but it's okay.
Yeah. So yeah, the last one is actually from this part is from Ampere. This part is from Maxwell. Okay, it's a thought experiment he did, and then introduced this term. And then they're actually quite straightforward. Okay, so we're actually making it even simpler is because for light, right, traveling in free space, the rho here is the density of charge. It actually doesn't depend on the charge anymore, right? Because like once you generate the light, which usually involve electron, and when the light is propagating, it doesn't matter if you have charge around it, right? So here we only study the light after it's generated, okay? After it's generated, it's propagating. We don't care how light is generated. So in this case, we neglect the term of the charge because it's not affecting our traveling light. Okay, and then the same is for the current right here. So whether you have current or not doesn't really affect the light. Okay, it's not like you turn on your electricity and suddenly the light bent. Okay, it won't do that. Okay, so also for the traveling light, we get rid of this. We get rid of this current term, and then become this. Okay, become this, and of course this is probably in the context of EM field. Is that you guys will learn that okay by doing another derivative on this one and plug in this, and then you will get a wave equation from the Maxwell equation, and then that wave equation would show you that EM field is actually can be an oscillation wave, and then the speed of the light is you can actually derive speed of light from there. And because this is a concept from another class, so I'm not going to go into that. Okay, so the question here is that okay, now if you look at this, it's a bunch of field, okay, or wave or field, depending how you want to call it. How can you make the connection with quantum, right? The quantum, the equation we know, for example, is the Schrodinger equation. Right, Schrodinger equation. It's a wave function, and then wave function represents the state of your object, and then its evolution is determined by the Schrodinger equation, which has Hamiltonian in it. Right. So a natural thought to connect the light to this Schrodinger equation is to try to write down the energy expression for the light, right? Because Hamiltonian here is representing the energy or the energy operator. So if you can write down the energy of the light, then there could be a way to link the light and the Schrodinger equation together by looking at the Hamiltonian. Okay, so here I'm just going to give it to you guys, and then you can look online or you can look on textbook of how to derive the energy of light or energy of EM field. Is that it's an integration of the electrical field square. Okay, here we're not using amplitude square is because electrical field and magnetic field, they're real numbers. Okay, they're real field. Of course, you can put e cosine something into exponential ix plus e to the minus ix. You can put them into complex numbers, but then in reality they're just real numbers here, real field here. Okay, and then so you have integration of electrical field square and then magnetic field square, and then integral over the entire space. Okay, integral over the entire space. So what it tells you is that your field actually has energy in it, right? And you can kind of feel it when you're under the sun, right? It become a little bit warmer, so that's the energy. Okay, so this part. In many books, they're called density of energy density of light. Okay, energy density of the EM field. And if you look at this, and then you try to draw a comparison between any other systems, the energy of other systems you have known before. So the form of this is that you have one variable and the square of that, plus another variable and square of that. Okay, so this is actually the same or very similar to the harmonic oscillator. Right, you have an object, and then its mass is m, and then the spring, the stiffness of the spring is k, and then the energy of this is kx squared. This is the potential energy of the spring plus 2mp squared momentum, right? That's the kinetic energy. Kinetic energy. So if you just look at this, you see that there's a similarity, okay, similarity between these forms. And then, of course, we will not jump in so to say, okay, so they're the same. No, we actually prove it here. Mathematically, they're exactly the same at the end. Okay. Any questions so far? Okay. So as in any of our previous calculation, we would need to do a few simplification before we can actually calculate anything, right? Like the previous example is the infinite potential well, which actually doesn't exist, but then we kind of have to have it, otherwise the math is terrible. And you can imagine the same apply to the light. If we don't add any constraint, then you can think about it is that then the light will propagate in the space, indefinitely, right? Just go from point A to point B and then keep going and then go to the infinite of the universe. So what that would do is that will make this integral impossible to calculate, right? Because the integral is integration of the entire space. And then if your light field is infinitely long, then this integral will naturally become, will go to infinity, right? So that actually won't work. Well, there's a way to make that work, but then the math is a little bit more complicated. So to avoid handling this minus infinity to infinity thing, what we would do is we would confine the light in a pair of mirror, okay, which form a Fabry-Pérot cavity. Let's see, put it here. So a pair of mirror, I'm not sure if you guys learned this. This is a Faber Pro cavity. And then we can assume that the mirror is perfect, 100% reflectivity, so that if there's a light inside, okay, it will actually be reflect back and forth within the mirror indefinitely. Okay. And the benefit of doing this is that, okay, we will be able to calculate this integral, okay, from 0 to L again, if the distance is 0 to L. Okay, we'll be able to calculate this without, worrying about the infinity. It's kind of the same idea that we apply to the we use in the infinite potential well. Okay, now let's think about how what the light would be inside the cavity, right? Inside the cavity. So so let's set the coordinate first. This direction is z. Okay, it's the light propagation direction, and then the vertical direction is x, and then the direction that coming out of the whiteboard is y. Okay, so it's actually a right hand. Okay, and some of you might know that in a lot of the EM wave, the electrical field and the magnetic field can be perpendicular from each other, right? So, for example, if the electrical field is on x direction, the magnetic field can be in y direction. Right, can be in y direction. So this is, you might ask, okay, does it has to be this way? No, but this is just simpler. Okay, simpler for us. So in this settings, we assume, just to simplify things, we assume the electrical field of the light is along the direction of x, right? So we write it down as this is the unit vector on the x direction, okay? And then we know that the magnetic field is in the direction of y, okay? And then the light is actually traveling along the z direction, right? So they're all perpendicular to each other very well, and then that way it makes things a lot easier. Okay. Okay. Any questions so far? Okay, now let's try to write down the electrical field inside the cavity. Okay, so you might wonder, okay, how can you possibly know that, right? Because, like, for example, in free space, you can the light field you write down is simply like e to the, there's a cosine omega t minus kx, right? And that's it. Right, and then this E is unknown, right, because it depends on the source of your light. For example, the sun is brighter than the light bulb, right? So the electrical field for the sun is much stronger. Okay, so here what we are going to do is simply to assume that there's an E, there's an electrical field, and then see that this is traveling light. See if you put that light inside the cavity, do you need to change any of your math there? Okay, and apparently, actually, one thing is very obvious here is that the light goes in two directions now. Okay, the light goes into forward direction and then backward direction, right? Because whatever going forward will be reflected back, whatever going backward will be reflecting this way. So that you can call the forward light E plus, and the backward light E minus. Okay, E minus, and they're identical, other than their direction. So then what we can work on that is that the E inside the cavity, okay, will be a function of z. Okay, when you go to different places, it will be different, and then a function of time, right? Because we allow it to, well, it's actually oscillating. And then by writing down in this, we actually assume that the light inside the cavity is a plane wave, right? It doesn't have any x or y dependent. It's like just a plane wave. And it can be written down as forward propagating light plus the backward propagating light. Okay, and then the forward light can be written down as, you have your, well, first is the field is pointing on this x direction, and then we assign an amplitude to it divided by 2. Okay, it's just for simplicity reason. And then it's the frequency and the propagation. Okay, e to the ikz minus I omega t. So here I want to explain a little bit that usually in quantum mechanics, for the light, we work with the negative frequency component. Okay, the cosine here So you guys learned it in the past is that if you write down a light, traveling light, you will write down as cosine omega t minus kz, and then the minus sign indicates that it's propagating on the forward direction. And this can actually be written as this, e to the I omega t minus I kz plus e to the minus I omega t plus I kz. Okay, so in quantum mechanics, usually we only calculate this part. And the reason is that if you guys remember the Schrodinger equation, when you solve Schrodinger equation, okay, the time-dependent Schrodinger equation, for every eigenstate, is actually equal to a distribution of on x and then e to the minus I omega t. Right. So it's just to keep it consistent with what we will use in the Schrodinger equation, okay, to have this e to the minus I omega t. And you will say, okay, how can I convert back into the real part? That's actually quite simple. You take the real part of this, and then it becomes cosine. So you return to the every time you want to measure the electrical field, you just take a real part of your function, okay, and then it gives you a cosine and return to it. And then depending on how you define the electrical field, sometimes you need to add a factor of 2 there. And the second reason to not use cosine is because for cosine and sine, when you do a derivative, it changes, right, from cosine to sine to cosine. It's a pain to keep track of those. Okay, so from now on, minus I omega t means the frequency of your light is omega, and then ikz means it's propagating along the z direction. And then similarly, you can write down the backward propagating light. That's also the field is along x direction, and then because what's going forward will also be reflected back, so that the amplitude is exactly the same. The only difference would be the propagation direction now become ikz minus ikz. It's the backward direction, and then minus I omega t. Okay, and one more thing is that you need to add a phase here. you need to add a phase, because when you reflect, okay, it's likely that the reflection of the light has a relative phase compared with the forward going light. And then later we'll show that this is actually arbitrary. This can be taken as an arbitrary phase just to make our math a little bit simpler. Okay. Now, apparently what we can do is that we can put the same term in the front, and then so you have ex e to the t, okay, and then e to the I k, well, and then e to the minus I omega t, okay, and then these two terms which are different is e to the I k z plus e to the minus I k z times e to the I phi, okay, divided by 2. Okay, so here you actually have a chance to make this extremely simple, right? Because if you guys remember, the cosine x equals to e to the ix plus e to the minus ix divided by 2. And then also, so if you choose phi to be 0, then you can actually return this to cosine. And then there's a second way to do this is to make it into sine, okay, is e to the ix minus e to the minus ix divided by 2i, okay, divided by 2i. You can do either way, and then here, actually people prefer to use sine. A simple reason for that is that, when you do derivative of sine, it doesn't have the negative sign. Okay, cosine when you do that, and here you can just choose, accordingly. Okay, and then also you see, okay, then if I choose phi to be pi, then there's a minus sign here, become a minus sign here. But then how do I add the I here? Okay, how do I add the I here? You can also see here the amplitude is just something we assumed. Right, we just write it down as this. You can add an imaginary I into the amplitude and then add imaginary I here. Okay, so there's many flexibility for you to play with. So eventually the net result is that under a certain selection of phi, okay, under a certain selection of phi, you have ex, et, okay, and then put it this way. Ex sine kz et e to the minus I omega t. Okay, this is just one type of selection of the phi. It doesn't have to be this way, but then this will make the math the most simple. Okay. And also, if you look at it, this is just what it tells you is that inside the cavity is just a sine wave, right? Just a propagating sine wave, which make a lot of sense. And what it really is that the forward propagating light and the backward propagating light form a standing wave, right? Form a standing wave. This is exactly what will happen if you try to play the violin or try to play the guitar, right? There are two nodes on your string, and then when the wave started, even if start, for example, start forward propagation, it will actually be reflected by the node, and then become backward reflection, and then they form a standing node that is sine wave or cosine wave. Okay, so this is exactly the same thing, but then just the math is a little bit complicated. Okay. Okay, and here. Okay, here what we will see is that, okay, there are two different type of variables here, right? Because in Schrodinger equation, you see that Hamiltonian is a function of position, and then this part is a function of time, right? So it actually makes sense to separate right here to separate the position term and then the time term. So what we will do is we will define this. Okay, we'll define this as Ex. Okay, Ex is the direction, and then sine kz. Okay, it's the same here, and then we call and then for this time-dependent amplitude, we put an amplitude out. Okay, the strength of the amplitude, we put it out as a parameter a, which is not time-dependent, and then we put all the time-dependent term into a variable called q. Okay, qt. So you can see that a times qt equals e times e exponential minus I omega t. Right? It's nothing special. We just make this definition. Okay, make this definition, and it should be noticed that you shouldn't read too much into what is A and what is Q, right? For example, especially their amplitude. For example, I can give another 2 to the A, right? And that's perfectly fine as long as I divide 2 in the QT, right? So these two, one of them can be treated as a free parameter. Okay, if you increase A, then you decrease Q. Overall, you make sure AQ equals this one. Okay, and later you will see why this is actually useful. And a spoiler alert, the Q here is actually position. Later you will see that. Okay, any questions?
What's the little e sub x vector representing?
EX, this one?
Yeah.
Okay, this is the unit vector. So because we're in three-dimensional space, right? Your electrical field has a direction. So EX simply means that it's pointing towards the x axis.
But it's propagating along the z?
Yes, of course, yeah. So, well, the way to think about this is a transverse wave. Right, there's longitude wave and transverse wave. Longitude wave means that your oscillation is along the propagation distance, which is like the sound wave. Okay, and then the longitude wave is that you go up and down while the wave propagate. You can think about it as water wave. Water wave has a component of transverse wave, right? So that's why people can surf, right? Because the wave actually go up and down while it's propagating forward, right? So this is exactly the same thing here. And just for the record, water wave is not a transverse wave. It's a combination of transverse and longitude wave. Okay, just to make that clear. Okay.
Could you repeat why we don't have to worry about the I in the denominator for when we make it sine?
You mean here?
Well, yeah, like when you change that E
Oh.
and all that into sine, you said something about the I in the denominator.
Yeah. So the actual thing we need to do here, if you think about what we avoid here, is that when you put this mirror here, you're actually adding a boundary condition, right? And then I don't want to go into discussion of that because that would take 20 minutes. Okay. So yeah. So what I was telling you is that okay, if you satisfy the boundary condition, then you will see this is sine, and then there's really no reason to go into that in this class. Okay. Yeah. Okay, so then what we can do next is that all the things we do is just to try to calculate the Hamiltonian, right? Try to calculate the energy, and then we see that half of the Hamiltonian, half of the energy is coming from the electrical field, right? So we can actually use this expression and then do this calculation, right? We say the energy of your electrical field, He, equal to integration from 0 to L, right? Because these are perfect mirrors, the light cannot escape. And then the term here is 1/2 epsilon, and then this, right? This. Then you have a square, which is a constant, okay? And then qt it's not position dependent, and then you have sine kz square again, and then the integration of the entire space or the volume will give you dx dy dz, right? Dx dy dz. And you can see that in this function, there's only z, there's no x and y, right? Because we assume it's plane wave. And you will see, okay, then there's a problem. If it's plane wave, it goes from minus infinity to infinity, right? But then we know that at least for lasers, it doesn't do that, right? Laser has a certain spot size. Okay, when you point it to something, you can see actually the size, what the size it is. So what we can do with this integration is that you can first put all those position independent term, outside of the integral. Okay. And then there are two integral here now. So you have one is from 0 to L. Okay. From 0 to L, this one is integration of z component. Okay. And then there are another two integration of x and y. Okay, x and y. So here, okay, this one you know how to do it, and then you can show that the integration actually, the result doesn't depend on k. Okay, this integration will give you L divided by 2, right? Just because it's sine square, and then when you integrate it, it's like doing an average, and then the total length is L, so it's L divided by 2. And then this one you can understand it in this way. Okay, this one is really representing. This one this one gives you non-zero value when there's light on it, right? For example, if your light spot is this, if this is x and y, if your light spot is this, right, then this integration is contributed by the value showing up inside, right, in here. Okay, so for example, your laser pointer is like 1 inch by 1 inch square when they illuminate on the screen, right? So what this integration shows you, if you look at the dimension here, it's length square, right? So this is area. The dimension of this integration is area. So what this will give you is the effective area of your beam size. Okay, effective area of your beam size. And if you're confused by this, this is actually fine, because again, the reason of this confusion comes from the fact that we say electrical field is not dependent on x and y. Okay, we assume it's plane wave, and then we're now considering the spot size of the plane wave. The actual way to do this is that you put x and y in it, and you can solve that. Okay, there's a Gaussian. Usually the beam looks like a Gaussian profile, and then you do the integration, you get the effective area. Okay, or the spot size. But then the way to understand this is really this integration just gives you the effective size of your beam. Okay, and if we combine all of those, and then you get this q squared t. There's a 2 there, and then you bring it from 4. And S effective times L. Right? S effective is the effective area coming from this one, and then L is from here. Now, if you look at this, okay, you have an area times the length. And what that is that's volume, right? That's volume. So what it really is the volume occupied by the light, which actually makes perfect sense, right? It's you have, if your field is the same strength than if you occupy more volume, right? Occupy more volume, then when you do the integration of volume, then of course your energy increase, right? So this one, these two in combined is effective volume, and then in total it goes to A square QT square V effective. Okay, V effective. Now, if we compare, well, because we say that the light, well, we already know the answer. The light, eventually, when you finish the calculation, the Hamiltonian will look exactly like the harmonic oscillator. So, what we need to do here is to actually try to make the form look similar. Okay. So for the harmonic oscillator, we know that you can either write down 2kx squared plus p squared divided by 2m. And then harmonic oscillator also have k equal to, omega, the harmonic oscillator frequency omega equal to k divided by m. Okay, if you use this to replace a k here, because for light, frequency makes sense, but then the k, actually you can't say the stiffness of the light, right? It doesn't really make any sense. So if you replace that, you get m omega squared x squared plus p squared divided by 2m. Okay, so then what we will do here is that q, okay, q here is a variable that, because all other things are just constant, right? Constant. Q is a variable representing how your electrical field change, and that will likely to be end up as the x, right? As the x. So then what we can do is that, because we know A is a free parameter, we already say A is a free parameter, then you can make the definition, of, you want 1/2 epsilon A squared V effective times Q squared T looks the same as 1 square m omega square x squared, right? If you want them to look the same, then your A has to be 2m omega squared epsilon V effective. Okay, so you can define your A in this way because your A is a free parameter. Okay, and after doing that, you will see your HE, the energy of your electrical field, is square and then Q square. Okay, and there's an obvious question here is okay, what is the M? Right, we introduce an M. So the way to think about M is that A is a free parameter, so the M is actually the free parameter that replaces A. Okay, it doesn't have any meaning. Okay, it doesn't have any meaning. It's just a free parameter, and later you will see that it actually doesn't mean anything here. Okay, M is a free parameter to replace A. Okay, and omega here we can assign an actual number for omega because we only need one free parameter. So omega here, we usually assign it to the actual frequency of the light, right? So that the meaning of the omega is the same as what people use in EM field. Okay, so okay. So let me further write down the electrical field. Okay, electrical field itself is AQ T, okay, equals to okay, just in case we lose track of where they are. Okay, any questions here? Okay. Now we'll go very quickly on solving the magnetic field because you can see the math should be the same because the electrical field and magnetic field, they have some kind of symmetry there. And if what we do is correct, and if the light is really in a mathematical form equivalent to the harmonic oscillator, then what you should see is that you should see the calculation of the energy of the magnetic field will show up like this. Okay, we don't need to define any more free parameter. It should show up just like this. Okay, and if it's not, that means the light is not the same with the harmonic oscillator. Okay, so the way to calculate the magnetic field is very simple because you have Maxwell equation, right? So once you select your electrical field, you can automatically get your magnetic field. And then the curl here is not that difficult to calculate because your electrical field has a certain direction and your magnetic field has a certain direction. Okay, and then you can look at the detail of the calculation in page 5 of the lecture note. Okay, and just to save time, we're not going to repeat that, but you can kind of predict what will happen if you go through this calculation. Is that this is your electrical field, and then on this Ampere law, then what you will see is that you need to do a differential on time, right? Differential on time. So your magnetic field, should have a term like Q, and then differential on time. So differential on time, we add a little bit, add a little dot, okay, on top of the variable, and also you have a curl on B, right? Curl on B means that whatever the function is, you need to do a differential on position, right? And then after that curl, you're actually equal to E, okay? E, so it's sine. So what you will see is that B, okay, you can expect in B the position function here should be something like cosine kz, right? Cosine kz. So when you do the curl, it becomes sine kz. Okay, so you can expect that. And then of course, whenever you do curl, there should be a 1 over k coming in the front, right? Because when you do differential, then you come out as a k, but then here you don't see k, right? So you should have 1 over k in the front. And then you have all this constant, okay? They should also get in there. So eventually what you will get is, okay, you will get mu naught epsilon naught and then A divided by K and then cosine kz and this one. Okay, you can do the math trying to use this curl, and then it will show you the exact same result. And then because of this, then you can again do this integral, right, to calculate the energy energy of the magnetic field is the integration of 2 mu naught 1 b squared dv, and then the process is exactly the same, right? You have all this constant, and then you have cosine, you integrate that, it becomes 1 over 2, L over 2, and then you have integration of x and y, and that gives you effective area, okay? So that everything is the same, so you can, I would just skip those steps and then tell you that the result is 4, okay? 4 comes from 2 squared here, no, coming from integration of cosine. Here there's a 2, and here's a 2, so there's 4. And then k squared, and mu naught squared, epsilon naught squared, a squared, v effective, and then q t squared. Okay, this is your energy of the magnetic field. So if you look at this, let's see if we can, for the harmonic oscillator, the kinetic energy can also be written as 1 over 2 mass and then speed, right? Speed squared. Okay. If you look at this, you say, okay, it doesn't work, right? Because although you do have the q, the speed of the q square, okay, same as x, right? But the coefficient is different, right? The coefficient is different. So that it's not a harmonic oscillator, it's a weird oscillator, okay? But actually you can simplify things and then it will show actually it's n, okay? So the way to do this is that, I'm not sure if you guys know this, but well, you guys will know when you graduate eventually. So the speed of light, okay, can be expressed as this: the magnetic permittivity and then the vacuum permittivity multiplied together is 1 over c squared. Okay, and this one you will be able to see that when you solve the Maxwell equation, trying to solve the Maxwell equation in classical wave. Okay, you will see that term here, showing us the speed of the light. Okay, and also another thing that we can use is, we know, well, we don't want to use k, right? Because k is actually related to the frequency, right? We know that k is 2 pi divided by lambda. Lambda is the wavelength of the light. And then we know that the wavelength of light can be expressed as speed of light and the frequency of the light. So k, a very convenient expression is omega divided by c, right? Omega divided by c. So if you do that, then you plug in all those, and then what you will get is what you will get is that there's a 4 here, okay, and this is 1 over c squared. I think here I made a mistake, c, yeah. Okay, 1 over c squared, and then down here is k squared, right? K squared is omega squared divided by c squared. So you can see that the c squared will cancel each other, okay? And then also you can plug in a, right? A squared v effective. We already know what a is. Let me just write it down here. A is 2m omega squared epsilon v. Let's see, I think I made a mistake here. Okay, so it's mu naught. Mu doesn't have a square here. Actually, mu square cancelled 1 here, and then epsilon is here. That's true. And then this one. Okay. So mu naught epsilon naught gives you 1 over c squared, and then you are left with another epsilon. Okay, you're left with another epsilon, and then you multiply a squared in. That gives you 2m omega squared divided by epsilon v, okay, and then times another v, and then q square t. Okay, you guys can do this calculation once and you will see that. So the speed of light cancel each other, epsilon cancel each other, volume cancel each other, omega cancel each other. So you're left with, and there's a 2, there's a 4, okay, so you're left with 1/2 m q speed of the q t, right? So you actually, after this simplification, you actually get exact same term as the harmonic oscillator, okay, exact same term as harmonic oscillator. Any questions here? No? Okay, good. So from this moment on, we don't need Maxwell equation anymore, right? Because we already use them to calculate the energy. So let me just erase it. And also the real reason that we don't need Maxwell equation anymore is because we already do the integration, right? We already calculate the entire energy here, so that the Maxwell equation is the equation of how the electrical field change in space change the magnetic field in time, right? So, but when you integrate it over the entire space, then you're kind of eliminating all those things. So what we will see now is that the energy of the light inside this cavity is 1/m square q square plus m q dot. Okay, and then you can also write down the electrical field. Let me just double check. Electrical field is Ex, okay, pointing upwards, and then sine kz is its spatial distribution, A qt, and then A is and then also the B, right? The magnetic field is Ey. Mu naught epsilon naught A divided by K cosine Kz, and then Q, the speed of the Q. Okay, so so we've done almost an hour of calculation and arrive at energy of the light. And then interestingly, we didn't use anything quantum. Right? So if you think about it, right, we're just calculating the classical energy of the light. So at this step, we didn't do anything quantum. There's no quantization whatsoever. And the quantization happens here with this argument. Okay. The quantization is this. So we know that for the Schrödinger equation, the Hamiltonian determines the entire evolution, right? So if you look at the Hamiltonian of the light and the Hamiltonian of the harmonic oscillator, they're exactly the same, except one is written as Q, the other is written as X, right? So if you apply Schrödinger equation, try to solve the Schrödinger equation, okay, and then the solution of X will be exactly the same as solution of Q. Mathematically, there's no difference. There should not be any difference. So in that sense, what you need to do now for quantization Okay, quantization is that it's the same as what we do for electron, is to make them into operator, right? Make them into operator. And for the position, it's very simple. X is just X. There's no change. Okay, X is just X. So it's the same for Q. Okay, and then the difficult part is the momentum, right? So the momentum is m q dot, okay, equals momentum, and then the momentum equals to h bar divided by I partial x. Right? This is actually where the quantization happens, and because your momentum is now an operator, the Schrodinger equation becomes the second order differential equation. Okay, and so it's the exact same thing when you do quantization of light. Okay, you put Q. The Q is just like the position. So when you act on a wave function, it just multiplies itself, right? Nothing special. And then you can also define a p, a momentum, for your light. Okay, that's also m times the velocity. That's p. And then you can make that into an operator, which is h bar divided by I partial x. Okay, so it's exactly the same process as how we quantization of electron, and then we do the same to quantization light. Okay, and before we go any further, okay, I want to say one thing is that normally when you look into textbook, they usually don't write it this way. Okay. What they do is that they usually don't write this down directly, because later I will show you guys this is not necessary. We don't even need to know the actual form for p, and then we can actually solve this Schrodinger equation. And in actual quantization, what people normally write down in, well, for example, textbook, is that they write down the commutation relationship between x and p. Okay. Commutation is defined as a times b minus b times a. Okay, this is a definition. And I don't know if you guys remember, in one of the homework, I asked you guys to calculate xp act on a wave function, is it equal to px on a wave function? And then most of you get it right? These two are not equal to each other. And this is a direct result of the fact that your momentum is a function. Well, sorry, your momentum is an operator, right? This is a direct result of that. And we can show it to you guys, okay, what is really equal to. So, for example, if you use x and p, and then you act on the function f of x, right? F of x. Then the first part would be, so first you all have h bar I, so you put it in the front, h bar I. And then you have x, and then partial x, f of x. Right, so this is the first part here. Okay. And then the second part is momentum x, f of x. So this is partial x, x, f of x. Okay, and you know that this is, you can use the chain rule, right? So it's very obvious here. The chain rule make this term into f of x plus, first you do derivative on x at comma f of x, and second is x and partial of x, right, using the chain rule. And then you see that this term cancel each other, but then you have a remaining term that doesn't cancel. Okay, doesn't cancel. And eventually the result is, okay, you put this in, and then there's a minus sign, so it's I h bar f of x. Okay. So what it means is that when something is an operator, you can't switch their order. Okay, you can't switch their order, and what I mean in a physical term is that if you first measure position and then measure momentum, your result will be different comparing to first measure momentum and then measure position. Okay, and later in next week we'll show you guys that this is actually this commutation relationship is directly connected to uncertainty principle. You can actually show that if the commutation relation is 0, then you don't have uncertainty principle. While your uncertainty goes to 0, but then if you have this, then you have the uncertainty principle. Okay, so overall, okay, because f of x is just any wave function, okay, that can be differentiable, so that you can write down as x p equal I h bar. Okay, so a lot of times the quantization process, people just say, okay, you have a Q, very well, you have a Q, and then you can define a P, okay, mq dot is P, and then the quantization is that you make them into operator, and then the commutation relationship is I h bar, right? This is called quantization, also called quantization. These two are equivalent. Okay, these two are equivalent. And actually, very often people use this instead of that, and then the reason you will see in the next class. Okay. And now we have 1 more minute. I want to briefly mention a consequence of quantization of light. Okay, is that because the Q, if you look at it, what is Q? Q is electrical field. The amplitude of electrical field is connected to Q, right? And then P is Q dot, right? Time differential of Q, and that's actually magnetic field. Magnetic field. So if we do this quantization, what it means is that the uncertainty principle will hold for P and Q. And because P and Q also is connected to energy, to electrical field and magnetic field, so that there's actually an uncertainty principle between electrical field and magnetic field. This is not something. Okay, larger than something, right? So electrical field cannot be 0 at the same time with the magnetic field. Okay, you cannot know both of them at the same time. And a striking consequence now is that if Q and P cannot be, well, because you cannot know them at the same time, so they cannot be 0 at the same time, so that your energy is always larger than 0. Right? Your energy is always larger than 0. So it means that even if there's no photon, okay, even if there's no photon, it's just vacuum, you still have some energy there. It's called vacuum zero energy, or vacuum quantum vacuum fluctuation. And this is something a little bit troubling, but then also very, very fascinating, because there are many effects you can observe from this quantum vacuum fluctuation. This is actually the reason that why you have lasers. Okay, there's you can actually calculate this fluctuation in electrical field. They can actually interact with the electron in atoms, and then make the atom to decay from high energy level to lower energy level and emit a photon. So the zero energy here, non-zero energy here, actually has physical meaning. It's not just a potential energy where you can shift and then make the energy go away. Okay, it actually have effect here. And then we'll talk about that later in the next class. And then this is all for today. Thank you.